Hey everybody, welcome back to Fastware. I know it's been a long time, but I hope you're not going to be too angry at me. Just decided to spend some time with family, enjoyed some COVID. Now, after all holidays and health returning, can actually return to create something. So today I have something just I wanted to share. A lot of people might not be fully aware of how alignment works, and I want to talk to you about how structs and classes in C++ are aligned and structured, what the size depends on, and how is the internal padding done. So this is the topic for today, and if you find it interesting, please remember to leave that like, subscribe if you haven't, and let's get on to it. So we'll start by creating a standard kind of a struct that you would do in C or C++. So we type in struct, and we have type, and what we'll have here, we'll just have a few simple variables. So we'll do int a, int b, bool c, bool d, pointer e. Right, so these are all primitive types. There is no complex types. So we want to understand the basics here. So let's crack on to it. So if you want to be kind of addressing into that structure, each of these internal member types have their own padding and their own size. So let's work these out. So you taking of the base address of my type, A would be at what padding? So we can play a little game. I ask you, you think about it, you actually write a comment or think to yourself in your head, and we can move on like that. So of the base pointer of my type, or a base address of my type, the int a would be at padding 0, right? Oops, sorry, padding 0. And it's going to be 4 bytes size. Now let's move on to int b. So what is the padding and what is the size? So if you guessed padding, can't spell, this is my problem, padding 4, and this is going to be 4 byte size, you are correct. Now let's move on to the next one. So I would say probably I'm wrong in saying that this is padding. Let's rename this to offset, which is going to be more appropriate, I think. So, so the Boolean C, what is the offset here? Think about it for a second. So if you thought to yourself, or you said that it's 8 and it's 1 byte, you would be correct. Now let's move to the double. So obviously what we were doing here before, you would think, okay, so it's 8 bytes plus 1 byte, so it's going to be at 9 bytes. But hey, here is where we're talking about alignment. Alignment of a double, so you align a previous type, so in this case bool C, to the alignment of this type. The reason why you do that, because the booleans need to be aligned to 8 bytes, and 9 is not 8 bytes, so it's not 8 byte boundary aligned. So therefore, what the compiler does for you, it inserts some padding right here. So it says padding 7 bytes for double alignment. So therefore, so this now starts at 16. So offset 16, and this is going to be obviously 8 bytes, right? So in the last one, since on 64-bit systems, which I would say most of the systems these days, but you might be working on architecture that is different, a pointer is actually 8 bytes of size as well. So, and here is 16 plus 8. this is going to be at offset of 24, and it's going to be 8 bytes. Right, wonderful. So now, what is the, if I would run size of my type right here, can you tell me what size this entire type is? So obviously you could say, well, the last offset is 24, and this is 8 bytes, so this is going to be 32, right? And you would be correct. For those who thought that it's 44188, which gives you what is 16, 24, 25, you were wrong, because that padding is inserted by the compiler, and it is enforced by the type. Okay, so this is one example of such a thing. Now let's say we want to avoid this padding. The only thing that we want to do is just move this boolean to the bottom. See what happens then. So we have struct my type 2, right? And let's do exactly the same thing here. Okay. Now we have double E, and we have our pointer E, and then we're gonna have this bool C, right? Voila. So let's not waste time. So we know that these two are 4 and 4. Now this one, it's 8 bytes and it's 8 bytes aligned, so therefore there is no padding. So we're good. So offset of 8 and 8 bytes, not bits, bytes. There we go. And voila, that looks pretty good. So now let's move on next. So what is the offset and size here? So if you said offset is 16 and 8, it would be correct. Now let's look at the last one. So this is 16 plus 8, so this is offset of 24, and it's obviously 1 byte. Beautiful. So did we solve our problem? So if I run size of my type 2, what would I get? Would I get 25? Well, I'm afraid not. You're still gonna get 32 bytes. Now why that is? The simple reasoning here is that any struct needs to be aligned to the largest alignment requirements of any member types that are inside. So in this particular case, both a double and a char pointer have a requirements to be aligned to 8 bytes. So therefore, my struct would be actually 25 bytes with 8 byte alignment. There we go. And therefore, that transfers into 32. Why I can't type today, I don't know. I'm sorry. But that's 32 bytes. However, there is a GCC, it's also respected on client. You have an attribute, which allows you to actually ignore this 8 byte alignment, which we have here. And that thing is, so you do it like that, and you're saying that this is packed. Now, this particular attribute ignores the alignment requirement or packing requirement. So attached to my type, this padding would be ignored. When attached here, the padding on the bottom would be ignored. And therefore, now both of these types would be 25 bytes in size. However, int, so when you have arrays when you have a single structure, it's fine. However, when you have arrays, in an example, such as you would have your my type 2 array of 10, in this particular example, since the offset here is 25, so the size of the structure, so when you index to the second element in this array, so the first is at 0, the second is at 1, this integer is not aligned to 4 bytes anymore. And it's going to be a problem because 25, so the offset in bytes is 25. And therefore, this offset 25 plus 0 is not 5-byte aligned. So the compiler has to issue the instructions to deal with address shifting and masking in order to extract the values. This is actually quite complicated and probably should not be used unless you know exactly what you're doing. But this is a tool, and I'm showing you how to use it. Okay? So, last example of these sort of things, which I would encourage you to use rather than both of these, either one wastes space and time and have their own problems, I would instead encourage you to use a struct of SOA type. Now, structure of arrays, which I talked about quite a few times before, is quite different from object-oriented model, where you have a type and you have a bunch of fields inside it. Here, instead, you have a type and you have arrays, where the index to that array represents a particular object. So in this particular case, you would have a pointer to A, you have int pointer to B, you have full pointer to C, you have full pointer to D, and you have char double pointer to E. Right? So these are arrays. And these beautiful arrays, now you're thinking how I'm going to be populating it, how the initialization is done. And I would show you how I do it. And if you want to play compiler or you want to write really well optimized code, let me demonstrate how to create initialization function for and destruction of SOA type. So SOA type can be initialized with this type of create function. I know it looks kind of threatening, but I'll walk you through, and hopefully by the end you will understand exactly what's happening here. So the count is how many elements do we need. So this is like a reserve function, let's say for your vector, or the size, resize or reserve function. So this is what it does. We start at the bottom. The reason is that the next type needs to be aligned by the type of the trailing type, right? So the alignment of the trailing type, sorry. So we start at E and we say just size of, and we say count. So how many? So we have E size, and then we say next type, which is double, and then we multiply by a count. We take the alignment requirements of a char pointer, right? And this is the align function. Given the size and alignment, it just aligns to that size. So we take number of bytes required for these doubles, alignment requirements of the previous type, and we align that, and here is number of bytes required here. We do exactly the same thing for Boolean. So this is the important thing here, right? Because we don't want to have this unaligned doubles. So we have a Boolean count. So let's say we have count 3 here. So this would be 3 bytes. But because the alignment requirements of double is actually 8 bytes, this whole thing would align to 8, it would spit out that C size instead of 3 would be 8, right? So that makes sense. And then we do exactly the same thing. So from the back, right? From the bottom to the top. Then we look at all the types available here, and we take the largest one. A compiler does that automatically, obviously inspecting all the member fields and saying, you know, max of all of these, and takes the maximum. But we can do it simply by saying that we know that it's a double, so this is the alignment. We compute the size, and then just introduce a little kind of an object called the union memory space, right? Which has a PTR and a UNPTRT address. The reason why I use these is because I don't want to do reinterpret casts in order to move pointers around. And this solves that problem for me because we know that these two are representative of exactly the same object. What we can do is just have a PTR and the address and a simple operator for instance, moving the address along or subtracting. You can add these yourself. And the reason why I do that is like that. So we initialize our memory space by saying that PTR will be equal to aligned allocation. So we want to align it with the alignment of that double and the size, which is the size requirement of that structure. Now here, what we'll have is we would static cast this void address, and this is our A. Now, next, we increment that space by the A size, so we offset it, and then we grab that PTR and that becomes B. And we do exactly the same thing for C, D, and E. And that's it. So I'm sure you will agree that after walking through this, this is not as difficult as it first may seem. And obviously destroy, because we understand our structure. A is the beginning address, which was returned from the aligned alloc, so therefore we can just pass it along to free. So this is fairly trivial. I hope you understand how compilers now pack and structure your types, your classes, and this would be my recommendation. This is the structure of arrays. The reason why I like it, because of its predictability and performance. Simple as that. There's no real other reasons that I would use it, because it actually increases the performance and reduces cache misses and whatnot. And to demonstrate that, let me run some benchmarks, as I usually do. So here it is. We'll run some benchmarks. So alignment effects, we scale with so from 10 to 100 to 1,000 up to 10 million. And as you can see, this is our timings. So we have effects 2, which is our packed structure. And this is the SOA structure. So as you can see, it's not much faster, because it cannot really get much faster. Come on, we're dealing with structs of 32 or 25 bytes, which are tiny in comparison and only contain few primitives. We don't have any large objects, which we don't use because the actual code uses every member variable when doing their kind of a testing, their benchmarking. So the only gain here is by better structure of the code. That's it. So you can see that right towards the end, at 10 millions, we start to teeter off. This takes what, 1.3. Where is the millions? Millions. So this is 13 microseconds, 12. This is 10 microseconds. So we can do a little better when using SOA. What I would like to do is run through perf stat, which I showed you before. And if you don't know what perf is, you can watch one of my videos. There will be a card above, so look for that. And let me just run this little implementation. So we have running alignment, we have a benchmark filter. We want to run only effects _1. So we say benchmark _1. And let's run that. Again, we run through all these timings, and at the end, per stat, we'll spit out this beautiful little table of information. So we have number of cycles, number of instructions, we have page faults, we have number of branches, L1 decached loads, so number of memory addressing requests, number of addressing misses, so the data cache load misses. It's 9%, which is huge. And if we look at it, we have 2.61 instructions per cycle, which is not bad, but we know we can do better. So let's run second one. And go. We're almost done. Voila. So we have, again, all of the same information, but now we run at only 2.39 instructions per cycle, even though we kind of miss less our memory address loads. It's still about 7%, and the previous one was about 9%, but the previous was able to execute more instructions per cycle. So looking at this, it doesn't look that much better, to be perfectly honest, this packed data structure. That's because it suffers from, again, using instructions to shift addresses in order to access that data. And it can be a real mess if you just introduce into your code thinking you will pack your structures, make it smaller. So if you don't know what you're doing with it and you're not an expert in the field, don't use it. Just wanted to show you that there is a tool like that if you're interested in learning more. Now, let's run the SOA example, which doesn't suffer from the packed struct problems, but actually contains data very closely. Now, you might be looking at this, which previously was highlighted yellow, that we only have a tiny amount, less than 1 million load misses. But previously, we had over 1 billion, which is a factor of 1,000, right? It's crazy. And it shows because we can actually execute almost 3.4 instructions per cycle. So this 2.4 and this was 2.6, and this is 3.4. This is a great improvement. And as you can see, it's exactly what we were aiming for. So I hope that you learned something about alignment, how it's used, and what's the best way to achieve alignment. SOA data structures, so use them. That's about it. If you're interested in watching other videos, there's cards at the end of this video, which will take you to other videos. So thanks for watching. If you liked the video, please subscribe, leave that like, and I'll see you next time. Have fun writing fast code. Cheers. Bye.